Good morning, good afternoon, everybody. My name is Andrew Coombes. I'm a product manager at ETAS in the York office in the UK. Just a couple of words on my background. I've got a DPhil in computer science, which has come from York University, where I was specialising in safety critical systems. And since that time, I've been working in the area of field application engineering, consultancy, product management, in the solution fields, the application fields of embedded systems, real-time systems, safety critical systems, largely around the tooling areas. And I've been based at ETAS since 2016.
Okay, thanks, Andrew. Warm welcome from my side as well. I'm Rohan Pandit. I am working as a product owner at ETAS and located at Stuttgart in Germany. About my background, I have a bachelor's degree in electronics engineering, followed by an MBA in general management. Regarding my work experience, I have worked previously in the industrial domain, and since 2018, I have been working with ETAS in the automotive security domain. So with that, let's get started with the webinar today. So on today's presentation, we have the following agenda. So we first start with the question about why virtualization. So what is the relevance of virtualization in the next generation of EE architecture? Then we move on to some basics about the RTA hypervisor and the virtual device extensions. Andrew will give an overview about this. Then we understand how we can define a VDE for an HSM. Then we look at some use cases which are relevant for the HSM using a hypervisor-based system. And finally, we end with a Q&A session. Okay, then let's start with the first agenda topic, which is why virtualization. So we see that the automotive world has evolved over time in terms of EE architecture. We observe a clear move from function-specific ECUs to a more domain-specific ECU architecture. This is being done mainly to handle the complex vehicle functions. And in future, this is expected to become more and more domain independent with a vehicle centralized approach and eventually increasing the number of functions that are then moved into the cloud. Currently, we are somewhere in this domain here with the cross or domain centralized EE architecture. Such an architecture leads to a consolidation of several functions, which means that there is reduced hardware and more software-based solutions. Virtualization plays a key role in such a system where you have a central domain controller with the ability to handle several complex functions. The consolidation of functions eventually leads to a cost optimization. So this is extremely important for all the OEMs. The new EE architecture, however, also brings along several challenges. Some of the key challenges that we have observed are significantly increased bandwidth demand for secure onboard communication. The second one being the security hardening for the next level attacker model due to the wider attack surface. And finally, crypto agility, which means that we need to update the crypto algorithms much faster than the new attacks arise and are applied. So this is about the question of why virtualization. Now let's have a look about what the new generation of hardware offers us as some of the drivers towards a virtual environment. So first one is the separate hardware cryptographic accelerators. So the new devices add support for these security IPs which means that the host core can then use the security IP to perform a crypto operation with the key management done by the HSM. What does this mean? This means that the performance is significantly improved while ensuring the security has been handled by the HSM. In a virtual environment, similar to a host, a VM could also then request for such operations to be performed on these security IPs. Then we have a strongly increased crypto hardware support. The new targets have extended support for additional crypto operations to be then performed on the hardware side itself instead of the current implementation on the software side. This is again a significant performance improvement to manage the requirements of a complex system in a virtual environment. Then we also have an increased program flash, which then can be used to set up a virtual environment in addition to supporting more and more features here. Then we have the virtualization support in hardware. Of course, this is a quintessential feature to set up a virtual environment, and all the new generation targets support this in hardware. Finally, we have the ASLD hardware design. So this is to support all the safety use cases to ensure freedom from interference. And this is extremely critical in a virtual environment where we need to handle safety and non-safety critical VMs in the same system. So these were the drivers. Now let's have a look how virtualization can be an enabler for the next generation vehicles. So virtualization enables ECU consolidation. So like I mentioned, with the new architecture, we have reduced the number of hardware by using a virtual machine based system. The user also has then the flexibility to combine legacy ECUs by reusing as much as possible. For example, if a customer is moving from an older target to a new generation microcontroller, virtualization offers the flexibility of combining the legacy ECUs with this new generation of ECUs. The second point here is mixed criticality system. So this refers to the modular design in order to handle safety and non-safety critical system, which means that we can integrate multiple ASIL or trust levels with a hardware enforced freedom from interference, and especially within the VMs. Third, we have the resource utilization. Here we can reduce the downtime of the system by optimize resource utilization. Let's say, for example, we have a failure of a single VM within a system, but this doesn't mean that the whole system is down, as this particular VM can still be having a failure, but the overall system can still continue to run as long as this VM was not a critical or safety relevant VM. Then we also have the third-party software integration. Currently, we have several software vendors which contribute towards an automotive ECU, and virtualization offers the option to support independent software update cycles for each of this VM without a need for a recertification, such that we can retain component level safety and security standards. So in general, what you get as a user is an optimized system design based on the resources addressing all these four factors. With that, I will then hand over to Andrew to continue with the further presentation.
Okay, thank you, Rohan. We've been hearing so far about the use of virtualization. What I'm going to be talking about now is the underlying mechanism for how we go about providing this virtualization. hypervisors have been around for a while now, providing a capability for virtualization for microprocessors. What's relatively new right now is the possibility is happening that allows us to provide a hypervisor for microcontrollers. We're starting to see virtualization capable microcontrollers appearing on the market. So, for example, we see devices like the Renesas RH850 U2 family, the Infineon Arix 3G, that's TC4XX devices, and also devices based on ARM Cortex R52 devices. For example, the NXP S32 RT family and the STM Stella, all of which open the door to a microcontroller hypervisor. So we have been working on RTA-HVR, which is a microcontroller-based hypervisor, which we've developed here at ETAS. It provides an extension mechanism as well, which we need to talk about. This is a way in which we can actually share resources between different devices, virtual machines, such as security devices like HSMs, as we'll see later. To start with some terminology, we have a hypervisor which is designed for microcontrollers that support virtualization. So microcontrollers, we're talking about devices that include an MPU for memory protection and not an MMU. So it doesn't provide the ability to actually virtualize address spaces, but it does provide the ability to protect address spaces. Virtualization support consists of two things. We're looking for two things. The first is the processor mode. So in addition to the user mode and the supervisor mode, we expect the processor to provide a third mode, a hypervisor mode, which runs above those two existing levels. The other element of virtualization is a two-level MPU. So that's a memory protection unit that can be programmed both at supervisor mode and be programmed within hypervisor mode. And of course, the programming for the hypervisor mode can't be overridden by the programming at the supervisor mode. So it runs guest software on a virtual machine. The guest software includes any software that is written to run on that particular microcontroller family, provided it's not accessing the hypervisor mode or the hypervisor levels of the MPU. In practice, this means that pretty much any existing standalone software can be adapted to run on these sort of targets with very little modification and with very little impact on performance. So it could include classic AutoSAR, which comes from potentially any vendor, software running on bare metal, or even other operating systems, again, providing we're living within the restrictions of not attempting to access the hypervisor facilities of the chip. So each of these guest softwares runs within a virtual machine. A virtual machine is a collection of resources. So it includes virtual cores. Within a single virtual machine, you could have multiple cores, or it may just be a single core. But each of these virtual cores will eventually map onto an underlying physical core. The virtual machine also includes memory in terms of RAM and flash, and also peripherals, which are typically handled via sort of direct memory mapping, but in some cases might also include peripherals. So what's going on is, of course, the hypervisor is allocating, is configuring the MPU to allocate regions of the to the virtual memory regions to the virtual memory, so that it can use those regions entirely. And then if you've got an operating system running inside that virtual machine as part of that guest software, the operating system then can operate at supervisor level, and it can allocate subregions from that memory to tasks that it's running to provide its own protection mechanisms too. There are some challenges with the MPUs. So for example, it might be that the MPU, the hardware of the MPU doesn't provide enough regions for what we want to achieve. So if we have too many different types of memory, or we may have the I/O memory map may mean that we need to divide it into a whole bunch of separate little partitions so that we can allocate particular I/O to one virtual machine and other I/O to another virtual machine. And in that case, there may not be enough regions, or it may be that the MPU regions are too coarse-grained, so that, for instance, it might not be possible to allocate an MPU region smaller than 64 bytes. And we need to get a finer-grained access in order to do what we need to access the peripherals from a virtual machine. So we can look at the mechanism around that in a minute. A typical system configuration is where we've got a number of virtual machines containing the guest software. So we can see here we've got a mixture of AUTOSAR, other operating systems, and bare metal systems, bare metal applications. And the number of virtual machines may not match the number of cores in the system. So the hypervisor will allow a system designer to create an architecture where we can just map from the virtual machines to the cores, including allocating system resources to the virtual machines as well, so RAM, flash, peripherals, and so on. So the mapping would then allow virtual machines with multiple physical cores. So we can see in this example, virtual machine 5 on the end maps onto 2 cores. It also allows multiple virtual machines to be mapped onto a single core. So we can see also here we have virtual machines 2 and 3. It's also possible. Okay. The other thing is, of course, physical. Sorry. We can create mappings to virtual devices as well. So there may be a virtual device that we've created that allows us to provide communication between the virtual machines. So each of the VMs can share data as if they were connected to a physical CAN bus, for example. The other thing we can do is we can adjust the mapping. So if during the design of the system or the early testing, it may be that the loading is not quite right, it's possible to reallocate cores, virtual machines onto different cores. So for example, here we see that VM5, we now have given it complete control over cluster 1, and VM4 is mapped onto core 1 along with VM2, VM3. What's happening on core 1 is we're using a time slicing approach. So each of the virtual machines gets to run on core 1 for a period of time, then switches to the other one. So it's running in a round robin schedule where each one gets a time slice. The amount of time that each virtual machine gets can be adjusted. So it's possible to allocate each virtual machine with different amounts of time. We are also working as a future release to look at reservation-based scheduling. So more sophisticated scheduling policies are possible in this kind of environment. And so it's possible, for example, to make use of spare time in the schedule to provide additional processing that as it's needed. Now, I've mentioned a little bit about I/O. In general, there's 4 main ways that we can conduct I/O in a hypervisor type environment. The first one is, frankly, the best if it's possible to do. So if it's possible to map the memory containing the I/O you want to access to the virtual machine using the MPU, then that's just means that you can perform direct hardware I/O. And I would hope that the majority of the time, this is how I/O would be conducted from a virtual machine. So it means that the virtual machine owns the I/O devices, that it's not sharing them with anyone else, that the I/O devices are mapped via the MPU, And access is just conducted as if there was no hypervisor at all. So you just write to the memory locations, you read from the memory locations where the peripherals are, and you receive interrupts directly from the underlying hardware as well to say that events have happened that require you to react to it. So that's our best case. The second case comes where, for example, there aren't enough MPU regions, or the MPU regions don't have the right granularity. So it might be that you have byte-aligned devices, but you need to share devices that are in adjacent memory locations between different virtual machines, and the granularity of the MPU regions doesn't allow for it. In this case, the hypervisor provides virtualization of the MPU. So you would make use of APIs provided by the hypervisor to say, please write this byte to this memory location, or read this word from that memory location. And as the request is made to the hypervisor checks that the virtual machine has authority to access those locations. And if it does, then it grants the access. So it provides a little extra overhead, but it gives you the flexibility of working around constraints on the MPU. The third case introduces this concept of a VDE, a virtual device extension. And what we're looking at here is a shared peripheral. So there may be devices on the hardware which maybe all of the virtual machines want to access, but there aren't enough devices for each virtual machine to have unique access. So one example of this could be an Ethernet controller. In that case, everybody needs to access the Ethernet controller, but only one Ethernet controller exists. The other example, which is especially relevant to what we're talking about today, is an HSM device, where there may be only one HSM device, and the API for the HSM requires assumes that only one piece of software is accessing the HSM at a time. We'll come back to that one in a few slides' time. The final case is virtual peripherals. So our most common use case for a virtual peripheral is to provide communication between different virtual machines. And we found that a very good starting point for this is to provide a simulated CAN bus. What this means is that each device communicates to its own each virtual machine communicates to its own virtual device, to its own virtual CAN, and communicates to each of the other virtual machines. Which means that if you've got a set of software packages which are already communicating over CAN, and you want to integrate them onto a single device running by a hypervisor, very little adaptation is required. So that's a big reduction in the effort of integration. So the last two cases we talked about there, the shared device and the virtual device, requires the use of this virtual device extension. Just to put some meat on those bones, the VDE is a plug-in to the hypervisor, so it works in a very similar way to a device driver in a larger operating system like Windows or Linux. So we can create virtual peripherals, we can manage peripherals that have to be shared between virtual machines, and it also allows for other activities that have to be done with hypervisor privileges. So a system management device might exist where you may want to have a VDE that has the ability to shut down VMs or restart VMs, or to perform other things that would not normally be possible from within a virtual machine. Just looking at the architecture of a VDE, or the APIs that a VDE needs to handle, there are four main classes of interface that the VDE has to look after. The first is the initialization. So when the hypervisor starts up, the hypervisor controls the initialization, the startup of each of the virtual machines, and also the VDEs So it makes a call to a VDE to make whatever initialization is necessary, and the VDE will presumably do some interaction with underlying hardware if it's making use of that. The second main cluster of interactions that the VDE performs is handling the service requests from the guest software. So as the guest software requests makes a call to the underlying VDE, it has to be able to handle each of the different calls. The VDE will also create interrupts that go into the virtual machine as well. The third class is handling interrupts and interactions with the underlying hardware. So if it's making use of, if it's communicating with the underlying hardware, then it will be providing that interaction. And the fourth one is a poke ouch is the name of the interface. It's really a cross-core signal from VDEs running on different cores. So, for example, if we're looking at this virtual communication that the VDEs are providing, when a virtual machine running on core 0 sends a CAN message, a virtual CAN message, in order to be able to reach the virtual machine running on core 1, one VDE will need to send a signal to the other VDE to say that data is being transferred across. I've talked a little bit about the idea of a system integrator, someone who's responsible for pulling the hypervisor together. In addition to creating the configuration and adapting this configuration and working out which resources each VM gets, the system integrator also has the opportunity to bring together code which adapts the functionality of the hypervisor to the specific use case that the customer has in mind. So this custom code is all able to run at hypervisor level. And there's three main classes of this code. So we have startup code, which allows configuration of the hardware before the hypervisor starts. So, for example, it might be necessary to configure firewalls or other SOC-specific devices. We also have hooks. So these are callbacks that happen from the hypervisor on specific events, which might be related to individual virtual machines. So it might be virtual machine starts, stops, suspends, resumes. It might be errors. So an invalid access, invalid MPU access is made via the via a virtual machine, or it may even be unrecognized interrupts. So an unexpected interrupt takes place. And the third class is the VDE, which we've already covered. Now that we understand a little bit more detail about the hypervisor, VDE, and the way in which they work, we can look at a little bit more detail about how we enable sharing of a HSM specifically between virtual machines. So what we have is the same sort of architecture that we've seen before. Our VDE is what's responsible for handling the HSM. So the HSM software, the host HSM driver, is the software that interfaces with the crypto hardware accelerator, which runs on another core, presumably. This driver, because it's running as part of a VDE, it's running at hypervisor level, and it will, in addition to providing the HSM host driver, it will support multiple sessions being run in parallel. Each of these sessions corresponds to one virtual machine. Then within each of the virtual machines, we provide an HSM shim. That's just a very thin layer which takes the HSM API and presents that to the guest software that's running within the virtual machine. And then as the API calls are made through the API, they're just simply translated into a service call onto the VDE. So requests are routed directly to the VDE. And what it means, the appearance to the virtual machine is they have complete ownership of the HSM. So that they're interacting with the HSM as if they're the only thing using it. So with that, pass over to Rohan to talk about use cases.
Okay, thank you, Andrew. So Andrew has explained about how we can define a VDE for an HSM. Now let's have a look. What are the different use cases in terms of security in a hypervisor-based system? So we have identified here some of the key security use cases which are in focus for a hypervisor-based system. So the first one is secure boot, which refers to the validation of software parts before booting up, so that only authenticated software is executed on the ECUs. This must be now extended to include the validation of the additional software parts, specifically for the hypervisors and VDEs. But this also means that the startup time will be increased due to this additional software parts which have been added in a virtual environment, and this needs to be managed by the HSM. Secondly, we have the chain of trust operations. Generally, HSM performs a trusted chain of operations using certificates. Certificates are used as an enabler for several secure access use cases, such as changing ECU lifecycle in HSM, unlocking the debug port, and most importantly, to perform a software update. In a virtual environment, this is critical in terms of the software update use case, where we might have to update the software on independent and individual VMs without affecting the other virtual machines in the system. Then we have the HSM and crypto services. This is referring to the performance improvement using the hardware accelerators for a secure onboard communication. In a virtual environment, we would have to leverage the capabilities of the new hardware which offer these HSM and crypto services to ensure a good balance between performance and security. Then we have the access control, where we have to ensure isolation between the VMs as well as independent update cycles of the VMs. We have to reduce the access using an MPU-based system. Especially in a virtual environment, we need to focus on implementing an access control system to ensure that access to critical resources are restricted to the respective VMs. Finally, we have the audit, logging, and monitoring system. This is mainly for the return analysis and diagnosis phase, wherein the user can log security critical events, which can then be used in the return analysis phase. In a virtual environment, we can log about the status of the various VMs within the system. And in addition, some critical VM activities which can be configured by the user can also be logged and then used for diagnostic purposes. So these are some of the use cases that we see in a system based on a hypervisor. Now let's have a look at one of these use cases in detail. So here we are looking at the trusted boot use case on an HSM in a virtual environment. Of course, this is only a proposed design which could be then further tweaked based on market requirements for performance and security. So if you see in this diagram here, all the blocks that are in the light blue shade here are the current setup, and the ones in the brighter blue are the new blocks that we have added now for the virtual environment setup. So first, let's have a look at the existing boot up sequence without any virtual machines. So You have the host core and the HSM core. So initially the HSM is booting up, and then it moves into the core application mode after a successful validation of its own software. In the next step, we have the HSM checking all the secure boot software parts which were configured by the user on the host side. And then after a successful validation, it will release the host so that the host can then start its own initialization. At this phase, we already have the validation results available, so there is an option to already treat those validation results accordingly. After this, the host has the option then to request to verify other software parts based on the priority. And after successful validation, the host can then move into the main operation mode along with the HSM. So this is what the current system looks like. Now let's see what we see in a virtual environment. So we would have the same route again. The HSM will boot up and move into core application mode after successful validation of the HSM software. Then in the next step, the HSM will check all the secure boot software parts on the host side, including now the new hypervisor software part. And after the successful validation of this hypervisor software part, it will move and release the hypervisor. Now, in this step, the hypervisor will request the HSM to validate the bootable parts of the virtual machines. And after a successful validation, it can then start the VMs. So now at this phase, we have completed the basic startup sequence. Once the VMs are started, they can request the HSM again to check the application part of the VMs based on priorities. And after a successful validation, it can then move into the main operation mode. So this is how a new system based on VMs would look like. So in summary, the security use cases in a virtual environment have the challenge to manage the complexities of the next generation of EE architecture while ensuring optimum performance and enhancing the security for future attacks. So with this, we come to the end of the presentation. Thank you.